couple more years to follow political economies and justice. This follows on work that we did in the previous 2 years on diversity, justice, and democracy. In everything that we do, we're seeking to identify really big, hard questions that, as a society, we need to wrestle with, and which can be addressed only by combining normative work, positive work, and policy work. And at different moments, we tend to focus on one or the other parts of that triad. So we had, for example, Danny Roderick, our first lecturer, coming out of the combination of positive social science and policy space and reaching towards normative dimensions and conversations. And then Martin O'Neill, who starts from the normative and talking about quantitative easing and the Fed and monetary policy and so forth, was reaching out of the normative and into policy domains. And tonight it's a great pleasure to have somebody who is really an extraordinary scholar in computer science, as well as a practitioner, really, somebody who crosses the lines of working inside of the academy and working in government and in governmental contexts and in industry, and who has been willing to take on the question of the normative consequences of algorithmic work and algorithmic dependency. And so it will be a great pleasure. I've known Tina for some time now and knew she would be great for us in our conversation because when I, at one point, was trying to write a paper on higher ed admissions and trying to explore the question of what it would mean to use a geographic lottery above a certain threshold of achievement for admissions, I needed somebody to help me think about algorithms, like how would you algorithmize that? And so Tina was the person we co-authored a paper in that space with Brandon Fadelston as well, who's sitting over there, philosopher. So at any rate, Tina is an exemplary computer scientist in being ready to dig into the normative dimensions of the innovations that are just transforming our world at just really astonishing speed. So it's a great pleasure to welcome her. She is an associate professor in computer science at Northeastern University here in Boston. She's also on the faculty of Northeastern's Network Science Institute. Prior to that, she was at Rutgers in computer science, and prior to that, she was a member of the technical staff at Lawrence Livermore National Laboratory. She earned her PhD in computer science at UW-Madison. And her focuses are in areas like data mining, machine learning, and applications of massive data from networked representations of physical and social phenomena. And her work has been applied to personalized search on the web, to statistical indices of large-scale scientific simulation data, to fraud detection, mobile ad targeting, and cyber situational awareness. So it's really quite a range of applications that have come out of Tina's work. So anyway, it's a great pleasure to welcome Tina Eliassi-Rad.
Thank you. So thank you, Danielle, and the Stafford Center for inviting me to speak to you. I am, as Danielle said, I'm a computer scientist. I'm not an ethicist or a philosopher, so take it easy on me. Computer scientists are very good at bastardizing things because we want them to work, so basically engineering them. But as Danielle said, I've been interested in ethical questions in terms of big data. A lot of my algorithms are being used in government and in industry. And so as I go along the talk, you'll see that there's all of these links of interdisciplinarity. And so for something like ethics of machine learning, or what I'm calling just machine learning, you really need interdisciplinarity between ethicists and policymakers and political scientists and computer scientists. So let's get started. You may have seen this XKCD cartoon about what is machine learning. And so it's a little cynical from my perspective, but there is a grain of truth to it. And one of the things that you will notice is that the words wrong and right are there, but the words wrong and right do not mean morally wrong or right. It just means whether you got, for example, the weather prediction correct, that it wasn't going to rain today. And so what I'm going to do is I'm going to start off with just giving you some background about where machine learning came from, what it is, above and beyond the XKCD cartoon. And so machine learning grew out of artificial intelligence. Artificial intelligence is a very big discipline. Nowadays, all the hype if you want to call it, that you're getting is because of a lot of the advancement that have been in machine learning. But AI is a very big field, like computer vision, robotics, planning, etc. They're all, search is all part of AI. And as you can see here, so machine learning has intersections, obviously, with computer science. It has intersections with statistics, with evolution theory, control theory, animal learning, and econ. And so one of the things to pay attention to is that all of the fields that are over here are all empirical sciences, right? Nothing about what you ought to do. It's just basically we have some ideas about the world. Maybe we have some model of what is generating the data. And we want to be able to do some prediction, and so on and so forth. So in particular, if you look at what kind of questions these fields are historically been answering, in computer science, we're interested in how we can build machines that solve problems. And what does it mean for a problem to be tractable or intractable? And then in terms of statistics, usually there's this idea that I have some data, I have some modeling assumption, and I want to see what I can infer, and with how much reliability, right? So reliability and stability of my results really matter. And then in machine learning, a lot of it has been, can I build a computer system that can automatically improve with experience? And what are the fundamental laws that govern learning processes? And I'll go into what I mean by learning in a bit. So where the place of machine learning has historically been within computer science are applications which are too complex for people to manually design algorithms. So this is where, for example, you want to do image recognition. And of course, there's lots and lots of cars. And so what you want to do is you want to be able to have a computer system that observes a whole bunch of cars and then can predict a new car, even if it wasn't in the set of examples that it originally saw. And the other one is the applications where you require some customization of the software after it leaves the sort of a factory, right? And so here is where you get things like speech recognition. So, for example, Siri or Amazon's Alexa should improve over time as it gets to know your voice. So Arthur Samuel was the first guy who coined the phrase machine learning. He had a very distinguished career where he was at Bell Labs and then University of Illinois, IBM, and Stanford. And he referred to machine learning as a field of study that gives computers the ability to learn without being explicitly programmed. And so he developed the first learning algorithm out there, and it was the Samuel Checkers playing program. And basically what this program did was it went on and played a lot of games and then memorized each of the steps and how much reward it would get. And then it would have a heuristic search called alpha-beta pruning to search the space. And so that's where it all started, this whole phrase machine learning that you hear. This is the takeaway home to mom, where machine learning came from. So now, what is a well-posed learning problem? I mentioned learning a couple of times, and since we're coming from different fields, I wanted to formally define it. In 1997, Tom Mitchell defined learning as a triple, where you have a computer program, and you're saying that the computer program is learning from experience E with respect to a particular task and some performance measure P if its performance on T, as measured by P, improves with experience. So what does this mean? Let's look at an example that I'm sure you're all familiar with. Suppose your email program observes which emails you mark as spam and which ones you don't. And based on that information, it's learning how to better filter spam. So the task here is to classify emails as spam or not spam. The experience is the computer actually observing you label this as spam and not spam, different emails. And the performance is what number or fraction of the emails is the computer actually classifying correctly, right? And you could do this for many different learning algorithms and learning tasks that come your way, which is like, okay, what is the task, what is the experience, and what is the performance? And usually when you look into it in terms of ethics, there's usually something wrong with one of these. And so I'll cover some of them as we'll go on in terms of, is the task probably properly formatted? Is the experience the right experience, or is it poorly being collected, and what the performance is? And if there's any questions, I'm happy to take it as we go along. So some success stories, right? So and I put it in quotation because maybe you think, for example, some of the recommendation systems that you're using are not very successful. But obviously, you've all heard about, for example, IBM Watson that defeated the best human competitors in Jeopardy. The other one that made the rounds was Google AlphaGo that this last year defeated the EuroGo champion. So computers are very good at playing these kinds of games. Then we have speech recognition like Siri, like Amazon Alexa or Google Go. Then there's image recognition where we're very good at figuring out whether there's a cat in an image or a cat in a video. Then there is speech translation. You may have heard about these Google headphones that you can put in. And for example, if you go to Japan and you don't speak Japanese, in real time, it's able to translate Japanese into English for you. And then there's a lot of work in terms of fraud detection. I'm sure if you're using your credit card, you get these alerts, is this fraud or not? Most of the time it's not. They bend over backward to protect themselves. But there's a lot of work that's being done on fraud detection. So for example, I did some work with the Belgian government where they have companies that intentionally go bankrupt and you want to detect them before they go bankrupt. And as you can imagine, when humans are involved, usually there are some patterns in terms of people come together, they do something, they disperse, they come together. And so we can track their footprints. And then there's the self-driving cars, and then recommendation systems. And I put in success stories, and there's more of them. I'm sure you have your favorite ones. Because, for example, with recommendation systems, I have a friend that after she turned 30, all the ads on Facebook were about losing weight. And my friend, who is female, does not need to lose weight and was very offended by it. And the only way she could get the ads to go away was to go into Facebook and change her profile to male. So, but in some sense, it's similar to like why we all get spam, right? There are people who are naive out there who do actually click on the spam and go there. And so what Facebook is playing in terms of that ad is that the average 30-year-old in the US who's woman probably wants to lose weight. And so they're not as personalized as they should be. And then the other thing I wanted to mention in terms of self-driving cars, and I was talking about task and experience and performance, right? So the performance for a self-driving car is to go from A to B, right, without breaking any laws. But it's not about whether the vehicle is somehow carrying this in a moral way, right? That if, for example, I'm sure you've all heard where if the vehicle is, it's called the trolley problem, right? Whether it will hit the grandmother or whether it will hit the child that is with her. So, but we have made a lot of advances. I mean, in terms of engineering, right? So computer scientists, we're very like happy. Look at us, we've done all this stuff. And a lot of it has to do with the fact that computers have become a lot faster. So I'm sure you've heard about deep learning. And the reason deep learning is so popular now is because machines are fast enough that you won't go gray while waiting for the neural network to actually train. There's enough data that when you get stuck in a local optima, it wouldn't be that bad. And then they pick really good tasks, right? Like image recognition and speech recognition and natural language processing, tasks that have a lot of commercial applications. So now moving on to ethical issues of AI. So just a little background in terms of machine learning, especially since there's a lot of fear-mongering out there, I feel like, in terms of machine learning. And it's nothing to be scared of, really. So now ethical issues of AI. So these are the top 9 that I got from an article that Julia Bossman wrote for We Forum last year. And I'm sure you can add your own to it. Some of them I'm not as concerned about as others, but I'm going to go through them, and I'm going to focus then on the racist, sexist robots. So unemployment. I know this was one of the main focuses for this year. So will the success of machine learning mean the end of work, right? And we've all been hearing about the threat of automation in terms of manufacturing, right? We have about 3 million truck drivers, and what are they going to do? And so obviously manufacturing with robots. The loan underwriting, maybe I don't need as many loan officers. There are very good face tracking systems right now, so maybe I don't need as many security officers. And so there's lots of different areas where this advancement in AI and information technology and machine learning can take jobs away. And today and yesterday, there was this very nice conference at MIT on the future of work. So if you want to hear the best people in the world talk about this, I highly recommend going to this website. And my slides are online. I have the URL up front. I'll have the URL at the end of the talk as well. And then the other one is wealth inequality. So the idea is that as the owner of an AI system or owner of this intellectual property, I benefit and I get all the money, and then we exacerbate the wealth inequality that we already have. And there's a nice article by Nicholas Yan at Harvard Political Review this last year on automated inequality that I highly recommend you guys read. But from that, there was this quotation to a Harvard Business Review article where Eric Bjornjosson said, the outcome shared prosperity or increased inequality will be determined not by technologies, but by the choices we make as individuals, organizations, and societies. If we fumble that failure, if we build economies and societies that exclude many people from the cycle of prosperity, shame on us, right? And I like this attitude, right, that we are in power, right? So we can make a decision in terms of how we want to set up our society and how we are going to deal with the advances that we've made in terms of information technology, etc. So the next one is called humanity, and this is how, basically attention is one of those things that cannot be outsourced. This phrase is by my friend Bernardo Huberman at HP Labs. And so Facebook is free, right? YouTube is free. And so the way that they make money is by vying for your attention. And so all the things that we're seeing in terms of clickbaiting and fake news and polarization and ticket addiction falls under this heading. And of course, a lot of people are working on this, especially after the election. And what is you're hearing now in terms of like Google and Facebook and Twitter going in front of Congress and talking about how, for example, some of the fake news reached 126 million Americans. So I have a friend who is a professor at UNC Chapel Hill. Her name is Zainab Tufekci. And she went to a couple of the Trump rallies. And after that on YouTube, she got these recommendations for white supremacist rallies. And they just got worse and worse and worse. And so she has this saying that there's nothing too hardcore for YouTube, right? Because again, they're vying for your attention. And so they think, well, if they ratchet it up, you're going to go and click on it more. So just being cognizant that they are, in fact, manipulating your emotion. I'm sure you all heard about the Facebook study a couple of years ago where it came out as, oh, they were trying to manipulate your emotion by showing different articles on your news feed. They were doing this A/B testing. And in fact, this last week at MIT, there was a nice conference on, it's called MIT Code on digital experimentation. So a lot of companies are using A/B testing to see whether you would stay on their site more right? And then they can get more ads and make more money. So then there's this thing called artificial stupidity. And this is where you are trying to fool a machine learning algorithm, right? So there's actually this game about going and fooling Google Cloud Vision API. So if you go to Google Cloud Vision API, you can upload images to its database. And so you can upload images of, for example, stop signs where the stop sign has been tweaked. And so then Google image recognition will learn from bad experience, bad data, and maybe the self-driving car will not stop at that stop sign because it cannot recognize it. And so this is a big area that the government especially is putting a lot of effort in, this thing called adversarial machine learning. And it breaks down into whether I'm going to attack your machine learning system when it's trying to learn, or whether I'm going to attack it when it's actually doing inference after it has learned. And so that breaks into this poisoning attack where I'm going to poison your machine learning algorithm, or whether after it has been trained, I'm going to try to evade it. So for example, I'm doing money laundering, and so I don't want to be detected, and I can give it hard examples so that then it wouldn't be as confident in terms of whether I'm doing money laundering or not. And then there are all these other things that computer scientists look at, like whether the adversary has a black box model of the machine learning system, whether the adversary knows something about the actual algorithm that you're using. That would be the white box model, or if it doesn't know, it's a black box model, and it has to just query it to realize what is going on. And so one of the tasks, for example, here that is of interest to computer scientists is that can I predict what kind of features you're using to learn about X, right? So if I predict what kind of features you're using to detect money laundering, then I can try to evade it a lot easier, right? So the other one is this evil genie. So this is the unintended consequences of either a poorly defined task or a faulty experience or data. And so there's a nice article that came out in Forbes 2017 that you can go and look at. I'm going to go through some of these quicker than others. The one that I don't really I don't want to say believe in. The ones that I don't sympathize with, I go more quickly. The other one is singularity, right? This idea that we're going to come across as super intelligence and then we're all going to be in trouble. And obviously there's a Wikipedia entry here, and there's lots of other examples here. And this is, again, one that I don't sympathize with as much. I was at an NYU workshop on ethics of AI, and one of the very prominent AI professors from Berkeley was giving a talk about provably beneficial AI. And he was going to solve it with this thing called inverse reinforcement learning, which is not important, but what is that he was doing it on a 2x2 grid world, right? 2x2 grid world is not really our world. And so I wasn't paying attention to him, and I was playing with my phone, and I put my finger too long on the button. And you know what happens when you do that, right? And what happened was he stated his theorem. It was about provably beneficial AI. And the theorem was that the machine will shut itself off when it feels that it will hurt the human. And exactly when he finished the statement of the theorem, my phone went off, saying, "Excuse me, I didn't understand that." The whole room erupted. This guy that I know personally, and I was sitting in the second row, he looked at me, he's like, "Shut it off." I'm like, wait, what happened? I thought it was supposed to shut itself off. But what can you do? The next one is security. This is obviously a very big application, this idea that you can weaponize AI, right? We have already been doing this with drones, right? And this idea of robot soldiers. And so whether it's in the physical space or whether it's in cyberspace, it's a very, very big deal. And there's a lot of people that are working on it. But usually when they work on it, they don't think about it in terms of morality, I must say, at least the ones that I know of. And then the other one is this robot rights, this idea that will robots have any kind of moral status? And so if they do, then how should we treat them? And this becomes more important as we age, and there's all this talk about robots that will be in your house and they will assisting you. And we already have kind of a weird relationship with our phones and our laptops, right? I don't know about you, but I talk to my laptop, right? If it doesn't do well, I shut it up harder, right? And so if there's actually a robot that looks like a human, then we need to be more careful about that. And so people are working on this. So finally, the racist and sexist robots. So I'm going to use the remainder of my time to talk about this racist and sexist robots. So this is an area that, in fact, computer scientists have been working on for a while. So one of the papers, this is not a typo, 1996, that they were interested in biases in computer systems. At the time, they were interested in airline tickets. And so there were certain systems that favored that if you were going to travel, that you would travel on the same airline throughout. Right now we have these like Star Alliance, One World, these kind of conglomerates, but back then we didn't have it. But now, for example, one of the things that we do have is if you are on government money, there's this Fly America Act, right? That you cannot buy a Lufthansa ticket, you have to go to United and buy it through them, right? So that a US-based airline would get it. And I'll talk a little bit more about that. There's a recent paper, I'm working my way up this slide. There's a recent paper in ICHCAI, that's the International Joint Conference in Artificial Intelligence, that was published by a philosopher and a psychologist that put a taxonomy in terms of algorithmic bias. And this is really what we need, right? Because obviously philosophers and psychologists have been thinking a lot about what is fair, what is just. There is a recent course this semester that started at UC Berkeley on fairness in machine learning. It's a really nice source of information. And then there is a series of conferences called FAT-ML for Fairness, Accountability, and Transparency that's been going on for about 4 years, where they bring people together and they try to look at the issue of racist and sexist robots. So I'm sure that you have heard of some of these stories, right? You kind of cringe about them. There was one last year about an Israeli company where they're saying that they can identify whether you're a terrorist or a pedophile from your image. And then there was, just imagine, right? There's another one that recently was this thing about gaydar that came out of Stanford, that a lot of people labeled it as bad science, right? They went and they scraped images from dating sites. And they started with like 300,000 images, and they went down to 35,000 images because they needed the images to be just right. And then on that set, they produced their results. And one of the things which is not clear is that they really learned whether you're gay or not, or whether they learned something else, which is, it seems that pictures of homosexuals on the dating sites are of higher quality than heterosexuals. So they may have learned that. And in fact, this is a there is a very famous example in machine learning called the tank problem, where they wanted to learn whether a tank was an American tank or a Russian tank. And basically what they ended up learning was whether it was sunny or not, because all the American tanks were where it was sunny, and all the Russian tanks, the images were when it was gray, because there's never sun, right, in the communist countries. So that's what they had learned. And there's lots of other ones, right? So there was this thing, the Nikon camera, where for Asians there was like, did someone blink, right? Very racist stuff. There was another one a couple of years ago where the Google photo tagging, it mistakenly labeled a couple that were African American as gorillas, right? So these are like, it's like, what the hell is going on? This is just horrible stuff. There's other things in terms of, for example, Google's speech recognition has a gender bias. They're mostly training on male voices, usually white male voices and females. Or, for example, Google self-driving car is very good in California, but it may not do as well in New Jersey with all the potholes. And then, of course, you've probably all heard about the ProPublica study of this company, Northpoint, that has now been sold to a Canadian company, where, especially after the 2008 economic downfall, where we went through a recession, people were like, how do we save money? And so they went to these automated risk assessment software. And so ProPublica did a study on the software that Northpoint was using. You may have heard of it. It's called Compass, for correctional offender management profiling for our alternative sanctions. Already doesn't sound good. And basically what it was doing is that it was giving high-risk scores to African Americans as opposed to white people. And what was interesting was that if you look at this, this table, it's called labeled higher risk but did not reoffend. So the African Americans, they were saying 44.9% of African Americans, it was giving them higher risk score, but they weren't reoffending, versus the whites, right? So it was being in favor of the whites. And then you have the other one, which was for labeled lower risk yet did not reoffend. You had the opposite, that they said that a white person who was arrested was of low risk and the person did reoffend. And if you just want steam come out of your head, you should go and actually read the ProPublica story. It is not a pretty one. And then there are other ones, like Microsoft released this Twitter bot, and it was all supposed to be for fun and games, and within 24 hours, it had turned into a racist jerk. And so they pulled it off. So there was this coordinated effort to make it learn bad things, which it did. And then Microsoft pulled the plug on it. And then there are other things that recently there was a Science article. There was also NIPS, the Neural Information Processing System, where people in computer science are very excited about mapping raw data into these lower dimensional spaces. They're calling them embedding. And so a success story here is that in this embedding, if you have a concept king and you remove the concept male from it and add the concept female to it, you get to another point in this embedding space where it's queen, right? And like, oh yes, that makes sense, right? I found a good concept space. But then what has happened is that there are all these stories in terms of where you have man is to computer programmer, or man is to manager, as a woman is to homemaker or nurse, right? So these biases that we have in human language in terms of, oh, a woman is mostly a nurse and not a computer programmer, come into play. And there are approaches that people are using in terms of correcting these biases, which I won't have time to go through right now, but if you're interested, come talk to me. So now, going back to that 1996 article, what were they talking about in terms of bias, right? This is well before Facebook, YouTube, etc. So they had identified 3 sources of bias. One was pre-existing biases. So this is like social institutional biases, social norms, attitudes, and practices. The other one was technological biases. This is basically whatever constraints or considerations that you have to give to the technology because of its limitations. And the last one was emergent biases. These are basically biases because of the context that the system is being used. And I love this quotation from the paper where they said, we conclude by suggesting that freedom from bias should be counted among the select set of criteria, including reliability, accuracy, efficiency, according to which the quality of systems in use in society should be judged, right? So they're talking about performance, that P variable in the well-formed learning problem. So now we get into how do computer scientists define fairness? Probabilistically, right? That's what we got. That's what we're going to use. So, and we have lots of parities, right, that we use in terms of definition of fairness. And so the idea is that the decisions should be, in some sense, probabilistically independent of the sensitive features or protected characteristics like sex and race and color and nationality. And so, for example, the probability of me saying that you're a high risk should be independent of your race, right? And there are many possible senses of this probabilistically independent. And so as I was saying, there's lots of parity definitions. We love these kinds of things, like probability of this, condition on that. And again, I won't be able to go through all of them. If you're interested in them, you can look at, again, the FAIR ML class at Berkeley. And some of them that I'm listing are actually computing the same thing. So precision parity and positive predictive value parity are the same thing. And some of them are just summation of the ones.
Can you say what those two are, just give us an example of precision parity?
Yeah, I'm actually going to talk about it next.
I think we ask questions later, probably. So I want somebody to do that.
Oh, sure. Yes. No. I will actually go to it in just 1 second, so that it will be clear. So, for example, since I'm not going to talk about it, demographic parity is just that the output of whatever machine learning system that you're using should be independent of the sensitive attribute. Or the accuracy parity should be that the output of the accuracy of the classifier should be independent of the sensitive attribute. And I will get to the precision parity in a second, because it comes up in this impossibility result. So no computer science talk is complete without an impossibility result. And so we have one, well, actually 2 independent teams came up with it. One is John Kleinberg et al., and the other one is Alexandra at CMU. And impossibility results, for those of you who don't know what it is, I'm going to go in detail into it. But just imagine that you can't have your cake and eat it too. So to talk about this impossibility result, I'm going to give you some definitions. So I have some features of an individual. Think about these as, like, let's say medical records, just as an example, right? And as you may assume that, I'm sure you all have been to doctors and have medical records, that there are all sorts of measurement biases in them. And then there is this group of attributes or features that are special because they're sensitive or protected, like sex and race. And so they may be ill-defined, and sometimes you can infer them from other features. So for example, if I know your zip code, I can predict your race and gender very accurately. And then there's this other variable called y, which is the true outcome. So this is, in machine learning, we call it ground truth, is whether you actually have cancer or not, right? So I have some features about you. These are your medical records. I have some sensitive features about you, like sex and race and let's say nationality. And then the actual outcome that I'm interested in is whether you have cancer or not. And then I have this machine learning algorithm that will use the input, which is x and a, to predict the value of y, which is whether you have actual cancer or not. And so we're going to make some simplifying assumptions. That's what computer scientists are good at. So we are going to assume that A divides the population into 2 groups for now. So let's say you have the whites and the non-whites, and then you have this machine learning algorithm C, and for simplicity, just assume that it will output 0 or 1. So it's binary whether you are predicting cancer. So if you are not predicting cancer, then it's 0. It will output 0, and if you're predicting cancer, it will output 1. And then there's the true outcome of whether you actually have cancer or not. And if you don't have cancer, it's 0. If you have cancer, it's 1. And so what the impossibility result says is that if you assume that there's differing base rates, that is, the probability of cancer among whites is not the same as probability of cancer in blacks, and that your machine learning algorithm is imperfect, right, that its accuracy is not 100%, then you cannot simultaneously have all of these parities that you would like to have. So precision parity says that the probability among whites, I referred to the set A as whites, the probability among whites where you have cancer, given that the algorithm predicted that you have cancer, will be the same as among blacks. That the probability of a black person having cancer, given that the algorithm predicted that they have cancer, is going to be the same as the one among whites. So that would be precision. Then there's true positive parity and false positive parity, and these are basically true positive rate and false positive rate that I'm sure you guys have heard of. So, for example, for the true positive parity, it's a probability among whites that the machine learning algorithm will predict you have cancer. Given that you have cancer, that probability is going to be the same among blacks as well, that there will be no disparity between them. And then you can look at the false positive rate as well. It's the same. So what the impossibility result is showing is that you can't simultaneously have all of these. And in a couple of slides, I will show you why the Northpoint, right, the one that ProPublica looked at, is not fair, right? It cannot satisfy all of these all at once. And B and C, in a paper, they call it equalized odds, and I like that term. So you could say that you can have precision parity, so fairness in terms of precision, and these equalized odds. So this is an example from the Kleinberg et al. Paper, and let's go through it because it will make this impossibility results more clear. So your task is to decide the risk that a person has in terms of being a carrier of a disease Y. And suppose that a higher fraction of women than men are carriers, right? That you do not have equal base rates. And so what their results, their impossibility results are saying is that you cannot find a test, there are no tests out there, where you can estimate this probability that someone is a carrier of Y and have all of these 3 different properties be satisfied. And so what you're going to get is you're going to get a probability estimate that is systematically skewed either upward or downward for at least one of the gender. This would be the group, right? I had broken it down into A and B in terms of race, but you can have it in terms of gender here. The other one is that the test will assign a higher average risk estimate to healthy people. These will be non-carriers in one gender than the other. And then what you're going to have is a higher average risk estimate to carriers of the disease in one gender rather than other. And so what makes this really an important result is that this trade-off among A, B, and C is not a fact about medicine or whatever domain that you're looking at. Is simply a fact about the risk estimates when the base rates differ between the groups that you're interested in. And so if we go back to this ProPublica and Northpoint, so ProPublica's main charge was that black defendants experienced higher false positive rates. And Northpoint's main defense was that their risk assessment score satisfied this precision parity or precision fairness. But due to the impossibility result, we know that Northpoint's algorithm couldn't satisfy these equalized odds. And so we don't have to do empirical work, right? We have a theorem that has been proved. And so there was disproportionately high false positives among blacks and disproportionately high false negative rates for whites. And so there have been recent attempts to address this problem. Now, of course, we have impossibility results, so we can't get around it. But Cynthia Dork, who's in the audience, a distinguished professor here at Harvard, has looked at fairness through awareness and this idea of group fairness. So people who are similar with respect to classification tasks, here is a machine learning task, like whether you have cancer or not, should be treated similarly. And so assuming that you have base rates, then treating everybody equally is a good move, right? So because we still want solutions, even though we have these impossibility results, this is one way of looking at it, even though you can't get around the impossibility results. Yeah?
The impossibility results apply, they don't apply solely to machine learning, right? They're just true of any algorithm.
So what are some of the solutions that people are looking at in terms of machine learning? And in fact, so this is very much machine learning thinking and computer science thinking, right? So this is, again, why we need people from other disciplines to come and help us in this effort. So one is just, I'm going to pre-process or massage the data to make it less biased, right? And so there's lots of approaches that have been treated, that have been proposed there, including how can I learn a fair representation of the data, right? So I have my data, I can represent it in different ways. And so one way would be that I want to have an encoding of my data such that I'm representing it well while getting around these sensitive attributes. And you can think of it in terms of these point clouds. So I have this kind of transformation into some topological space that I know a lot about. It goes into like applied math, and I won't go into it. Or for example, you could have these role spaces, some of the work that I have done in terms of actually looking at the functional roles that somebody has in society and trying to make decisions based on that. There are these work that has been done in terms of statistical parity in cluster assignments. This is, again, putting groups of people together that are similar into these things we call clusters. So the next would be to actually change the algorithm itself. So you will penalize the algorithm to encourage it to be more fair. So you can either, for example, regularize the weights that you're putting on the sensitive attributes, how much they count. And so this could be either during training or during post-processing step. And you can think of this also in terms of, for example, I'm going to put some constraints on the learning. And then the other things that people are looking at, it would be that I'm going to allow the algorithm to use these sensitive attributes or protected characteristics during training, but during inference time, when it's actually being used, I'm not going to let it use these attributes. And then finally, people are looking at causal inference here, because you can look at counterfactuals and, you know, setting all other things aside and just tweaking one variable, what would happen. And they're very powerful, but they tend to be very brittle. And so moving on, you may have heard about regulations. This is lawyers and governments putting on regulations, especially in the European Union. There's a new set of rules that are coming in terms of general data protection regulation, where as a human being, you could go and you can ask for a logical explanation of why something happened to you, right? Why the algorithm decided that you are of high risk. And so you can read a lot about it. And it's interesting, when I talk to my European friends, they're interested in how it's going to actually be implemented, because as you can imagine, it's going to have a big impact on the IT companies that operate there. And then the last part of my talk is about the last question I asked in the abstract, which is, can you have just machine learning in an unjust world? And so we have these racist, sexist humans. We have biased judges. Was it better if you get sentenced by a biased judge than by a biased algorithm? I don't know. But we already have these kinds of stupid algorithms or stupid rules that exist, right? So we have the 3-strike laws. We have the mandatory minimum sentencing, right? And so these don't take any kind of empirical data into account. And so where machine learning can actually be helpful in terms of personalization and context awareness. So some of the things about Northpoint, when you look into it, they released like 132 questions that they ask people when they score them. And So they rate something like education very high. They rate whether you're homeless or not very high. So those are the certain features that they are rating very high. And so one can work with that. Even though, again, we do have the impossibility results, but at least one can try to be, quote unquote, more fair. So where do we go from here? There was a nice opinion piece in New York Times last week by Israni, and she said, computers may be intelligent, but they are not wise. Everything they know, we taught them, and we taught them our biases. They're not going to unlearn them without transparency and corrective action by humans, right? Which really struck a chord with me, that again, we are in charge and we can decide how to do better. And so to do better, right, we need to come together and have interdisciplinary action, right? We can't have all the different kinds of fairnesses that one might want because of the impossibility results. And so we need to come together to talk about what kind of fairnesses we want to optimize. As I said, computer scientists have been looking at it in terms of probabilistic definitions of parity. And we go back and look at our own performance metrics that we like: precision, true positive rate, false positive rate, etc. But if I talk to an ethicist, maybe I will learn to evaluate my system in a different way. So thank you for your attention. My slides are up there, and any questions I'm happy to take.
We've got two microphones on the sides of this.
So thank you for this. I'm trying to get my head around how bad this impossibility theorem is. So let me give you a parallel of another impossibility theorem that turned out to be not quite as bad as it seemed. And my question then will be, is there work of that sort on the radar here? And so this other thing that I have in mind is Ken Arrow's impossibility theorem in preference aggregation, in a way the mother of all impossibility theorems. Right? So what you have there is you have a bunch of individuals that have nice rankings of candidates, and you want the group ranking to have similar features. In particular, you want it to be a linear ranking, just like the individuals are. And that's not always possible. Right? So sometimes you get circles, basically. So that sounds pretty bad, because it seems like we can't have, generally sensible voting when there's more than two candidates involved, right? But the way this turned out to be not quite as painful as at this general level it seemed to be is a condition on this theorem is that there's a universal domain. So it is supposed to work for every way the electors would rank the candidates, right? And if you have intelligent domain, so you can explore what kind of domain restrictions would not generate that result, and that is actually very reassuring, because in many cases, not any profile will be on the radar anyway. So something parallel could happen. Might be the case here, that you can't have fairness in all these dimensions, but maybe you can find conditions under which, say, the likelihood of an unfairness in one of these sorts is fairly low, or maybe the deviation from the absolute fair result is fairly small. And in principle, judging from what you have said, it's quite possible. So what you said is consistent with this sort of thing solving most of the problem. Now, these are 2016 theorems, so maybe this is just beginning, but is there anything like that on the radar that might give us reassurance about this sort of thing?
Yeah, I think it's Cynthia's work on group fairness. Would it address that?
What we talk about is actually individual fairness. Rather, group fairness is these group properties that you're talking about, like equal false positive rates across groups, or statistical parity. Individual fairness is the idea that two individuals who are similar with respect to the classification task should be treated similarly. It's a completely different notion than group fairness. If the groups are very similar to each other in a certain mathematical sense, then individual fairness will in fact imply group fairness. But if the groups are very different with respect to each other, as in having very different base rates, for example, then that won't happen. So I think that the problems that were identified by Choldachova and Kleinberg, Mullainathan, and Ragaman are very serious and very, you're not going to get around them with these kinds of relaxations. Also, Kleinberg et al. Looked into that and showed that the negative results hold even if you relax. So, so our approach gives a different definition, and it of course can't circumvent the impossibility results because they're impossibility results, but it gives a different view that, you know, either you might or might not be able to live with.
So in terms of the group fairness, I can define my groups differently, right? So I think it goes back to the relaxations. And so usually, like, we have these clear-cut groups, but if I actually define my groups differently, like we know, for example, in terms of race or other kinds of things, people are treated differently if they're lighter skin or darker skin in reality, right? So I can have different types of groups as opposed to, so if I have a hierarchy of groups, can I do something? Where, as you said, so there's individuals that form these groups, but to bring some relaxation in terms of what. I see.
I don't know the answer.
I see. Because she's the person who would know it in terms of relaxation. Just wait until like 2018, and she'll come up with it. But I think it's a good idea. As you said, it's very, very new theorems that have been come out. So.
I have a question about probabilistic understanding of fairness. And basically the question is whether or not there's a way of understanding fairness in this probabilistic sense that would tell you whether a probabilistic sense of fairness is the kind of fairness we should be interested in. So let me give an example. Suppose that you're looking at how much insurance companies charge people for life insurance. Generally, if you get pricing that's actuarially fair, then people who have the same risk of dying prematurely would pay the same amount for life insurance. Now let's say that a company looks at part of the market, which is the market for low-cost insurance, $10,000 policies. And they find that the cost of getting information that would allow them to distinguish levels of risk would swamp any profits that they might get by distinguishing levels of risk. So they just put out ads and they say anybody without a medical exam will sell you one of these policies, same price. So the result is that people with very different levels of risk are paying the same price for their $10,000 insurance policy. Now, that's not actuarially fair, given the sense of it, right? People are not being treated similarly who are similar, but it's not unfair. It's just a business decision, for Christ's sake. So, you know, the people who buy it and say, gee, you know, I had a lot lower risk than my neighbor, and they paid the same price I did, I'm outraged. It's just not unfair, because that's not the kind of, you know, that sense of unfairness has no meaning in this context. All right, now, how would you know whether or not a probabilistic understanding of unfairness is what's at issue in a given case? So how would you know if it said, yes, it was unfair, if no, it wasn't? In the probabilistic sense, how would you know whether it was unfair, period?
Yeah, very good question. I mean, so you can think of it in terms of also, some people think affirmative action is not fair, right? In terms of preferring one group over the other. And so I think this whole notion of how would you define fairness and how would impact the society, and whether like these kinds of probabilistic fairnesses that we are defining. Again, as I said, like machine learning people, we usually evaluate our methods in terms of precision, in terms of recall, right? In terms of true positive rate, false positive rate, accuracy, right? And so we just took those and just said, okay, well, we're going to use them, the ones that we already use. Right? And so your question is very nice in that are there other ways that I can judge that my machine learning algorithm is doing well, right? So maybe for that business, they don't care that they have high-risk people and low-risk people all in the same group, right? And so in that case, then the performance P of how I'm going to evaluate my machine learning algorithm changes, right? And we can definitely change that. And so part of what has happened is that, again, we're just using the metrics that we normally use, which is whatever we can draw from what we call the confusion matrix, right? Whether it was true and I predicted it true, and whether it was false and when I predicted it false, or that kind of a thing. And all the measures are derived from that. So I think, yeah, I don't have a good answer for you, because it will then depend on the specific task and what the company or society wants the machine learning method to be judged on.
So there's sort of a deep question there about the role of the concept of prediction, right? Because the prediction would have to be defined in a different way in order for a different concept of fairness to be working in the machine learning process of connecting the task to the experience and the performance.
Right.
So the prediction is, just because of the ways the disciplines have grown out of each other, prediction is so close to connected to probabilistic reasoning. But that's the sort of set of concepts that you got to start, and so it would be a kind of interesting re-engineering of a kind of basic concept to figure out how to harness a different concept of fairness to the concept of prediction.
Yeah, and I think like one of them would be like judging your machine learning system in terms of, is it providing the best explanation, right? And not in terms of like precision or recall, but that it provides you the best explanation for why it thought this person should have a high risk assessment score, right? And so those become tougher to evaluate. But, and we usually, at least at this age of machine learning, we're not as interested in explanation as we used to be before. So.
Well, I have like 2/3 of the way up the stairs. Yes, I apologize. I'm sure I should maybe know that.
Great. Thank you very much. Lots of interesting points. I was particularly struck by your slide towards the end, thinking about, can there be just machine learning in an unjust world? Mm-hmm. And so this is just basically a thought and maybe a question on your reaction to it. So I'm not sure what kind of cases you were thinking of, but what struck me was the idea that in a scenario where the existing sort of non-AI ways of operating are already unfair, there's some kind of bias. It might be that adding AI reduces the number of people who are affected by that unfairness. So you might, realize that a certain group can be excluded. There's another basis for predicting that's more accurate. And it's not clear that that's improvement in terms of fairness overall. It might be that, now there's a smaller group that's being unfairly treated, and the fact that it's a smaller group makes the situation more unfair from a societal perspective. So I was wondering, for example, in the computer science literature, how people tend to think about those issues. Whether there's an assumption that you measure fairness in terms of the number of people affected, or you look at sort of relative sizes of groups that might be discriminated against or not.
It goes back, we really care about predictive accuracy, because that's where we made our bread and butter. So oftentimes it's not thought that way. But one of the things which is interesting, so again, Kleinberg et al. Did some work with the Arnold Foundation, because the Arnold Foundation also has its own system for risk assessment. And so it turns out that judges, when they make decisions about bail or not, they also take into account, for example, how crowded the jail is, or how many people they have already given bail to, or if it's before lunch. I'm sure you've heard these kinds of stories as well, where the algorithm wouldn't take that into account, right? So the algorithm, it's very specific in terms of, so what is my mission in terms of giving bail or not? Will the guy flee, or and will he commit another crime while being out, right? Now, of course, like with Northpoint, they are using all these other things as proxy in terms of, will the guy commit another crime? And like they're saying, well, if the education level is lower or he's homeless, he's more likely to, and whether they're good proxies or not. But I think you ask a very good question. Again, it goes back to maybe other ways of measuring fairness above and beyond just predictive accuracy, like something that grows out of a confusion matrix in terms of precision recall, accuracy, so on and so forth. And I don't know, you ask a good question, like as a society, I guess we can poll here, like would we be okay if a smaller group of people are being treated, I guess, more unfairly than if I had a bigger group of people and they were treated unfair, but not as much unfair? I don't know. Which one? Scenario one, small group of people, really unfair. One person. I think I'm with you, actually. And then large group of people, but not so unfair. Oh, again, I like it. It's not me. I question, sorry.
So this is another question about fairness, but it's really the question, why do you even use the vocabulary of fairness? Why do computer scientists talk about fairness if they're going to define it this way? Because it strikes me that there is intuitively a big fairness issue if somebody's race is being used as a predictor of whether somebody's going to commit a crime. If the question is whether somebody has cancer, or imagine the question is whether some particular treatment for cancer is likely to be successful or not successful. That would be a situation in which anybody might think the accurate predictor would be all that any sensible person would care about, and there would just not be any fairness concern whatsoever in that situation in the way that ordinary people would use the term. And so why do computer scientists define fairness in the terms that you say that they do, and how much thought has been given to the actual relationship between what people think about as fairness in other contexts and the definition you're using for purposes of doing your work?
Yeah, good question. I don't know, actually. The thing about it is that, so I guess, the first word that comes to my head when I read the ProPublica story is that this is very unfair, right? And so I think, in terms of the actual word fair, and that, for example, why is it that African Americans are not being given bail and are given such high risk assessment scores when, like, their background doesn't show it. And so they have all these different comparisons in terms of what people got in terms of high and low score. Other than that, I really don't know why they call it fairness, or they use the word fair. Again, the key thing to emphasize here, and I'm going to repeat myself, but that machine learning, especially in the context I mentioned, is called supervised learning, right? Where I have some input and I want to predict some y. And so we assume we have some ground truth. Like, for example, I can not give you loan, right? Or I can give you a loan and then I see that you actually default on it, right? And so then I have what we call a ground truth, and I can see how well I predicted or not, right? Or I give you a loan and you do pay it, and then I see, okay, how well I did in terms of, I can improve my algorithm. But I'm not sure I understand the question in terms of, like, why we use the term fairness. Because it seems to me like the ProPublica story is clearly unfair, that based on race, this is what's happening, right? I don't know if I answered your question.
Thank you. This is really fascinating. I want to go back to Dan's example, but as a way of thinking through what of this is about just machine learning and what of this is about fairness or unfairness or justice and injustice in terms of how we structure our collective social lives and when we take various things into account when we make decisions. So the impossibility result applies for any attempt algorithmically, that we can't achieve all three of these results simultaneously, whether or not it's through machine learning or through any other means, right? Which means that, and so where it feels to me as if machine learning is specific in this ethical problem, as opposed to being just this general ethical problem that when we try to use statistical results to make decisions about how to privilege or disprivilege people, right? It seems to be about our social choices to privilege machine learning outcomes, right? So that we might have said before, okay, when I rent you an apartment, I don't know anything about you. I'll do a standard background check and then I'm going to have to guess, right? And we know that there's lots of racism in how people guess, right? And it may well be that the machine learning outcomes are actually better than that, right? So Northpoint may actually be better than if you go and send people out and do, the apartment rental checks. It may be that with the Northpoint results, actually more Black people will get to rent apartments than in the absence of that. But it's still clearly wrong, right? It gives way too many false positive for Blacks and way too few, right? In the absence, sometimes though, we do the equivalent of throwing a dart because we feel as if we have no way to make a guess. So, we roll the dice or whatever. And my feeling is that this fairness issue, the justice that we're thinking about, is when we might be socially in the position where right now we just sort of roll the dice, we have a lottery, we say, we basically randomly allocate privileges and other things because we truly feel that we can't know. And now with machine learning, we have this illusion of knowledge. And so we then privilege what the machine is telling us and then work in biases that then prevent us from doing the equal treatment. That is what you're suggesting. I'm just curious, and this is obviously new, I'm curious what you think about that and where, if at all, you think it's the machine learning itself that's causing any ethical issues, or it's just about how we socially construct machine learning to give us truth and predictive power that actually we shouldn't be doing.
So, excellent question. There's multiple parts of that. So the thing is, the algorithm itself is not biased, right? The algorithm can amplify whatever biases that's fed into it, right? And what it's fed into it is whatever data that it's seeing, and partially it's historical data that can be biased about, there's not as many women professors in computer science and so on and so forth and so on, right? So there's historical data and it doesn't look at the root cause of why, for example, that may be the case. So a lot of it is from my perspective as a machine learning person, somebody who designs these algorithms, I don't think of them as biased. I think that the problem is the society and the data that I'm getting. And in fact, this is why one of the solutions is massaging the data, right? So that the data I give to my nice algorithm is not racist, sexist data, right? And so that's one aspect of it. I think again, getting away from just this prediction, the power of prediction to power of explanation may be something that we need here. Because if I have to explain, right, because what's happening now, for example, with the Northpoint is that the judge gets to see the high risk assessment. But I bet that most of those judges don't even know what the algorithm is using, what the features are, how much weight those features are getting. And in fact, in studies that in interviews that they did with those judges, the judges said that yes, the assessment score did change my mind, and I upped my the amount of jail time I gave to the guy, right? And I feel like if there's more explanation about why this assessment score was given, that the judges would do the right thing or the righter thing. So.
I just think for folks in the middle of the room, if you're worried that we can't get the mic to you, raise your hand anyway and you shout, okay? If that's keeping you from raising your hand. Sometimes unworking hands around.
Hi, thank you so much for your talk. I have a lot of thoughts and I'll try to be articulate with my question. So I think all of the questions have touched around questions that I also have. But I want to frame my question into more thinking about machine learning is affecting what is happening right now, right? These algorithms are it's happening very quickly. So my question is more towards like what can we do now to sort of like rein in some of these new discriminations that are being built into the system. So like I have a lot of worries. One of the concerns is like, it's great that we are doing these, we're trying to measure fairness, but like, what do we do about the fact that like, there are a lot of new discriminations that are being built into the system. Some of them we don't understand because like, we don't know what the impact is right now. And then in addition to that, like with the example that you gave about Facebook and your friend having to change her age, and then also GDPR's requirement on transparency, like, is that possible? Because my instinct is to say, no, that's not possible, right? Like we can't ask an algorithm to tell us exactly what it is deciding, and then like it is basically changing continuously. So what do we do now that we're living in a society in which like the machine learning algorithms and data is constantly changing the world that we interact with? Like, how do we push back on the, like, I guess, like, robot system that is now impinging on our social society?
Right. Do you want to put me out of business? Is that there's a couple of things. So you can ask a machine learning system to explain itself. It's just that those machine learning systems oftentimes are not as predictive as, for example, a deep network, right? In terms of whether a cat is here or not, right? So there are, so for example, you can look at a Bayesian network and you can try to reason over it. You can look at a decision tree and you can reason over it. So it's not the case that there are no machine learning systems out there that you cannot reason over. And in fact, when you work in applications in medicine, they oftentimes want an explanation, right? Now, I think the question goes back to, one of your questions goes back to the question that was here, which is, are you okay with the biased judge who is making those decisions, or are you okay with the algorithm that we're trying to improve, right? And I mean, in terms of a call to action, it's basically trying to talk about this different notions of fairness, right? And maybe pushing computer scientists out of the box that they're comfortable with in terms of evaluating their systems to maybe more explanation-based approaches, which used to be actually popular, back in the 80s, and kind of fell out of favor because of predictive power. But basically what happens is if you have okay, I have a phenomenon and I try to model it. If I want to do really well in terms of prediction, I have to basically model every nook and cranny of it. But if I'm interested in just description of it, I don't need to do that. I can just give you a nice broad description of what is happening. And so there is a trade-off there, and it's just a matter of, pushing the society in one way versus the other.
I'm sorry, I'm going to go on. We don't have tons of time left. There are lots of hands, so Susanna.
Thank you so much. In the debates about racial profiling, there's the position that says it's totally fine. And then there's the position that says, well, statistically it's fine. Like the proxies that are used, it's, give you a good statistical correlation, but it's morally not okay. And then there is a position that says it's sort of wrong twice over, both because the proxies, aren't really good even statistically, and also, even if they were, it wouldn't be okay to use them. And I was just wondering whether, your criticisms of what's happening with Northpoint, which of these positions is it most like? So is it that you're thinking there's something wrong with the proxies that were being used, or were you thinking that there is this mathematical problem, which is that even if the proxies were a little bit analogous to, well, I'm a woman, so I'm more likely to get this certain disease, just for mathematical reasons, if we put this into an algorithm, we're going to get exacerbated, we're going to get this exaggerated, like way more false positives in the end, like won't really be reliable. So is it more, do you see what I'm asking?
Yeah, no, absolutely. I think it's both. So I have problems with both of them. And I think that, so for the second one, because of the impossibility result, it's for that particular definition of fairness. And so if we move away from it, maybe we can do better, right? Or if we give it time, Cynthia is going to solve it. right? So it's gonna come up with a different notion of fairness. I have a lot of faith in Sophia. But I have problems with both because some of the solutions that computer scientists have looked at is that perhaps the data I have, I can map it to another space where in that space I don't have these bad proxies, right? That perhaps we can live in a world like as John Lennon said, right? Imagine where like there's no race, et cetera, and I'm just really judging somebody based on the relevant features and not based on race or education or, but I have problems with both.
In my role directing the Stanford Center, I discovered another impossibility result, which is that it's impossible to have both the fairness of getting all the questions answered and the fairness of respecting people's time and concluding on time. So let's thank Tina for a wonderful lecture.